They tell me there on the top of the page that many quantities in geometry and physics, like area, time, temperature, can be represented by a single real number. Other quantities, like force and velocity, involve both magnitude and direction and cannot be completely characterized by a single real number. So to represent that type of a quantity, you need a directed line segment. So basically you need a length, but you also need to indicate a particular direction that is going. And so in that case, we're going to have an initial point and a terminal point. We need to see where did we start and where did we stop so that we can see the direction that we're going. So let's say that I have this vector right here, PQ. For this vector PQ, we've got our starting point, our initial point is going to be P, and our stopping point, our terminal point, is going to be Q. So we'll call this P1, P2, and we'll call this Q1, Q2. All right, so if I want to give the component form of that vector, component form is just my stopping point minus my starting point. And it makes a difference if I say vector PQ or if I say vector QP, because that indicates a totally different direction. Also, a way that we'll know that we're working with vectors is notice that the symbol that they're using here, it kind of looks like an arrowhead, but the bottom part of the arrowhead is missing. So that's how we'll know we're working with a vector quantity. So to put this in component form, I could go through and I could say, okay, Q1 minus P1 and Q2 minus P2. So that's what we've got over here. Q1 minus P1, Q2 minus P2. That is our component form for that vector. Again, we don't want to accidentally look at this and think that we're talking about an ordered pair. And so when I have the component form of a vector, you'll notice that they're going to put, it almost looks like a little sideways V. So that's an easy way to remember that I'm talking about a vector. Also, when you see something in the textbook that is in bold print, when there's a letter like V in bold print, that also represents a vector when it's in bold print. If you're looking for a vector in standard form or in standard position, then its initial point has to be at the origin in order for it to be in standard position. There on 445, they give me some formulas. They tell me that the magnitude of a vector is just its length, and we're going to represent that with, kind of looks like two absolute value bars around the vector. So it's like two sets of absolute value around it, but that's how we represent magnitude or length. And that formula should look very familiar. What's that the formula for? Distance. Yeah, that's all it is. So you also have that program in your calculator that computes the distance formula. It'll compute your magnitude as well. If you've already gotten your vector in component form, then you can skip the long form here and just square each of those values that you had for your component form, because you've already found the change in the first values and the change in the second values up here when you got it into that component form. If when you find your magnitude you get an answer of 1, then that means that you have a unit vector. It's called a unit vector because it's only 1 unit long. If when you find your magnitude you get an answer of 0, that means that you have a 0 vector. And that's also represented with like just a bold 0 sometimes. Then we'll know that's the 0 vector. So the first example that we want to look at, and again these numbers that you see here in parentheses are going to be the examples that the homework problems that correspond with that example. So for the first example that we have here, we want to look at how to find the component form and the magnitude for this vector. So we could go through and say, okay, if I want the component form, so for the component form we could go through and we could say Q1 minus P1 and Q2 minus P2. So for Q1 we had 5 and for P1 we had 2. And then for Q2 we had 3 and for P2 we had 1. So that would give us a component form of 3, 2. Now you can also find your component form with common sense. You literally can come over here and look at, okay, if I start right here, How far over horizontally did I go? 1, 2, 3. How far up vertically did I go? 1, 2. Okay, then that's a component form of 3, 2. So you can also do it with common sense. You don't have to use the formula. Then they asked me for the magnitude or the length. So again, that's just my distance formula. And because I've already found the component form, I can just plug in the 3 and the 2. So I'll have 3 squared plus 2 squared. So my magnitude then is going to be square root of 13. Then they asked me to draw an equal vector. All right, if I'm going to draw an equal vector, that just means that two vectors are equal if their component form is the same. So all I'd have to do is start anywhere I want to and draw something that has the exact same component form. So for instance, let's say that I start down here at -1. As long as I go over 1, 2, 3 and go up 1, 2 so that it would have the same component form, I'm going to get a vector that has the same length and goes in the same direction. So I can really pick anywhere I want to start. This time I'm going to start over here. Go over 1, 2, 3, go up 1, 2. There's an equal vector. This time I'm going to start up here on the y-axis. Go over 3, up 2. There's an equal vector. So all of those would be equal vectors. All right, then over on page 446, they talk to me about vector operations. And they tell me that we can add vectors, we can scalar multiply vectors, we can subtract vectors. So let's look at some of the things that we can do there. There are actually two different ways that we learn in conceptual physics to add vectors. There's a tail-to-tail method, sometimes called the parallelogram method, and there's a head-to-tail method. So let's use the same two vectors every time. We're going to use vector u right here, vector v right here. Let's use those same two vectors every time. And in the first case, we're going to go parallelogram method. All right? For parallelogram method, I'm going to leave the two tails of the vectors together, and I'm going to make them the two sides of a parallelogram. And then I can follow those two sides to create the other two sides of my parallelogram. My answer is going to be called my resultant. Resultant, that makes sense. My answer is going to be called my resultant. And it's going to be from my starting point where my vectors were tail to tail, I'm going to go across the diagonal of that parallelogram that I drew. So my resultant is right here, u plus v. All right, let's add them a different way. This time I have vector u and I have vector v, and this time I want to go head to tail. The reason it's called the head to tail method is I'm going to take the tail of the one vector and put it on the head of the other vector. So I've created an equal vector here, just like we were doing a moment ago. And so when I go through to draw my resultant this time, again, I'm going from my starting point to my stopping point. So you'll notice it does not matter which of those two methods I use, I'm going to get the exact same resultant for u plus v. All right, let's look at scalar multiplication. Let's say that I had 2v. If I have 2v, it's going to be exactly what we would anticipate. I'm just going to take vector v, and I'm going to make it twice as long. So it's going to keep going the same direction as it was. It's just going to have twice the magnitude. If it was 3v, it would be 3 times as long. If it was half v, it would be half as long. A negative of a vector is going to be very much like what we were just doing with polar coordinates, where if you have a positive radius that's going this way, then a negative radius just goes the exact opposite way. Same idea with a vector. If this is a positive u, then this is a negative u. You could think of it as a scalar multiple as well, like you could think of it as multiplying by a -1. It's going to make it the opposite of each of those values. So then I could go through and I could subtract 2v minus u if I think of it as 2v plus a negative u. These two are already tail to tail, so I'm just going to go ahead and use my parallelogram method. So I'll use those as the two sides of a parallelogram. And my resultant will go from my starting point across the diagonal of that parallelogram that I've drawn. So we could use logic and common sense in drawing these out to come up with the answers. We also could find them algebraically using some formulas. So here's what they give me for formulas for doing the same things that we were just doing. If you have vector u and v in component form, here's a formula for u plus v. Add the first values, add the second values. Here's a formula for scalar multiplication. Just take k times each of your values. Here's one for a negative of a vector, -1 times each of your values. And then here's subtraction. Subtract the first values, subtract the second values. All right? So first I need to get these in component form. So I'm going to take those same two vectors we were just working with. Let's start with u. So if I do component form like we did higher up on the page, 3 minus 1 and 2 minus 0, then I'll get vector u is 2, 2. Or you also could have just counted over and counted up. Vector v, I'm going to do first value minus first value, second value minus second value, and I'll get -1, 1. Or again, you could have just counted over and up. So now that I have their component forms, to add them, I just add the first values and add the second values. And so I would get 1, 3 for my resultant. Okay, how is that answer algebraically the same thing that we got graphically a little higher up on the page? Well, let's look at it. If you come over here to this black line, if you start at your initial point and you go over 1 and you go up 1, 2, 3, that is the component form of that resultant. That's exactly what that is. All right, what if we did 2 times the vector? Then we could go through and say, okay, that would be 2 times the first value and 2 times the second value. So that would give me -2, 2. And sure enough, if I come back up here and I look at where we drew 2v, if you go over -2 and you go up +2, that is the component form of that vector. All right, look at the next one, 2v minus u. We've got 2v right here. We've got u right here, so let's just subtract. So we'll do first value minus first value and second value minus second value. And that gives us -4, 0.